Hello friends, welcome back. Today we are solving largest rectangle in histogram problem. First we'll start with reading the problem statement and then we'll look at some examples. Next we'll discuss the brute force approach to solve this problem that has the runtime of O of n cube, and we'll optimize this brute force approach to make it an O of n squared algorithm, and we will optimize it even further to make it a linear time algorithm, which is the most optimal solution. And finally, we'll write the Python code for the linear time algorithm. Let's get started. Given an array of integers heights representing the histogram's bar height, where width of each bar is 1, and we have to return the area of the largest rectangle in the histogram. Here is an example input array heights, where each element represents height of a bar in the histogram this input array represents. For example, 5 is height of the bar at index 2. In this histogram, we have to find the area of the largest rectangle. Let's look at some of the rectangles that are present in this histogram. Here is one rectangle whose area is 2 times, which is height of the rectangle, and 4 is the width of the rectangle, which is 8. Here is another rectangle where height of the rectangle is 1 and width is 6, so the area is 6. Here is another rectangle where height of the rectangle is 5 and width is 2, so the area is 10. Which is the largest rectangle possible in the given histogram, and that's the right answer. Let's look at the brute force approach to solve this problem. Here I have taken a different example, and the largest rectangle in this histogram is this. And the area of this rectangle is 2, which is the height of the rectangle, and 5, which is the width of the rectangle, so the area is 10. The brute force way of solving this problem is to look at all the index pairs. For example, 0 and 1 is one index pair, 0 and 2 is another index pair, 0 and 3 is another index pair, so on and so forth. Let's look at the pair 0 and 2. These indices act as the left edge and the right edge of the rectangle. Next, we go through heights of all the bars within this range, and we find the minimum height among them. For example, in this pair 0 and 2, the minimum height is 3 among 3, 4, and 5. And that will be the height of the rectangle formed by the index 0 and 2. So we can calculate the area of the rectangle formed by these indices 0 and 2 as minimum height multiplied by the width, where width is right index minus left index plus 1, because each bar has width of 1. So the area is minimum height in that range multiplied by the number of bars. And we repeat the same for all the other index pairs and finally return the maximum area. So in total, there are n squared such pairs, and for each pair, we have to find the minimum height, which takes O of n time. So the total runtime complexity of this approach is O of n cube. We can optimize this brute force approach to make it an O of n squared algorithm by making a simple observation, which is each bar can act as a minimum height for some rectangle. What does this really mean? Let's consider this bar of height 3. This bar is the minimum height of the rectangle formed by just the index 0. It is also the minimum height for the rectangle formed by index 0 and 1. It is also the minimum height for the rectangle formed by the indices 0 and 2. Similarly, if we consider this bar of height 4, this bar is the minimum height for the rectangle formed by just the index 1. This is also minimum height for the rectangle formed by indices 1 and 2. Finally, let's consider this bar of height 2, where this bar is the minimum height for the rectangle formed by just the index 3. This is also the minimum height for this rectangle. It is also the minimum height for this rectangle, and it is also the minimum height for this bigger rectangle. So what we are seeing here is we can keep extending either to the left of the bar or to the right of the bar as long as height of its left bar or right bar is greater than or equal to the minimum height. So the simple optimization we can do here is consider each bar as the minimum height and keep extending to its left and to the right until we find a bar whose height is less than the height of the minimum bar. And that will be the largest rectangle that can be formed using this bar as the minimum height. So the area will be minimum height, which is the height of the current bar, multiplied by r minus L plus 1, which gives the number of bars in the current rectangle. So there are total n bars in the given input array, and for each bar, we extend to the left and to the right until we find a bar whose height is less. So that takes off n time. So the total runtime complexity of this optimized approach is of n squared. Next, let's look at optimizing this further to make this a linear time algorithm. In the previous approach, for each bar as the minimum height, it takes off n time to find the left edge and the right edge of the maximum rectangle with this bar as the minimum height. We have to reduce this from of n to of 1 time. By that I mean, for each bar as the minimum height, we need to find the left edge and the right edge of the maximum rectangle formed using this bar as the minimum height in of 1 time, constant time. The way to do that is using monotonic stack, where we store the heights in the increasing order. Let's look at how this works. We start from index 0 and the stack is empty for this index, so we add this bar to the top of the stack. So height of the bar is 3 and index is 0. Next, we go to index 1. Since the height of this bar is greater than height of the bar at the top of the stack, which is 3, so we add this bar to the stack. Height is 4 and index is 1. Next, we move to index 2. Similarly, height is greater than height of the bar at the top of the stack, so we add 5 to the stack. 5 and 2. Next, we move to index 3. All we have done so far is we keep adding the bars to the stack as long as height of the bar is greater than the height of the bar at the top of the stack. We do this because if we consider this bar at the top of the stack as the minimum height, to find the left edge of the largest rectangle that's formed using this bar as the minimum height, we just have to look at the previous bar in the stack, because these bars are in the increasing order of heights, so the previous bar's height is definitely lower. And that forms the left edge of the largest rectangle. And we can do this in of 1 time. So coming back to the algorithm, we are at index 3 and height of the bar is 2. 2 is less than 5, which is top of the stack. So this bar at index 3 will form the right edge of the rectangle formed using the bar at the top of the stack as the minimum height. So the left edge of the rectangle formed using the bar at the top of the stack is the previous element in the stack, and the right edge is the current bar because its height is less. So the bar at the top of the stack is 5, and its left edge is the previous element in the stack, which is this bar, and its right edge is the current bar, which is this. So the rectangle formed using 5 as the minimum height is just this. So the area of the rectangle is 5, which is height of the bar at the top of the stack, multiplied by right edge, which is the current bar whose index is 3, minus the left edge, which is the previous element in the stack, and its index is 1. Since we cannot include the current bar of height 2 in this rectangle, we subtract 1 from the width. So the total area is 5 times 1, which is 5. So we can remove this bar from the stack now. So the new top of the stack is this bar 4. So the current bar has height 2, which is lower than the bar at the top of the stack. So the current bar will be the right edge of the rectangle formed using the bar of height 4. And the left edge is the previous element in the stack, which is the bar over here. And the rectangle formed using this bar of height 4 as the minimum height is this. And the area of this rectangle is the minimum height, which is 4, multiplied by right edge, which is 3, minus the left edge, which is 0, minus 1, because we cannot include the current bar in this rectangle, which is equal to 4 times 2 is 8. Now we can remove this bar from the stack. Now the bar at the top of the stack is 3, and the current bar's height is lower, so therefore the current bar will be the right edge. And the left edge should be the previous element in the stack. Since the stack is empty, we consider the previous element as minus 1. So minus 1 will be the left edge. And the rectangle formed is this. So the area of this rectangle is minimum height, which is 3, multiplied by the right edge, which is 3, minus the left edge, which is minus 1, and we subtract minus 1 because we cannot include the current bar. And the area is 3 times 3, which is 9. Now we can remove this bar from the stack. As you may have noticed already, for the bar at the top of the stack as the minimum height, we can find the left edge and the right edge in just constant time, which is O of 1. Now that the stack is empty, we can add the current bar to the stack, whose height is 2 and index is 3. Next we go to index 4. Height of this bar is 6, which is greater than the height at the top of the stack, so we add this bar to the stack. Height is 6, index is 4. Next, we go to index 5. Height of this bar is 1, which is lower than the height of the bar at the top of the stack. So this will be the right edge to the rectangle formed using the bar at the top of the stack. So top of the stack is this bar of height 6, and the right edge will be the current index, and the left edge will be the previous element in the stack, which is index 3. So the rectangle formed is this. And the area of this rectangle is the minimum height, which is 6, multiplied by the right edge, which is 5, minus the left edge, which is 3, minus 1. And the area is 6. We remove this bar from top of the stack. So the current top of the stack is this bar of height 2. Again, the current bar has height 1 and it forms the right edge. So the right edge of top of the stack is this, and there is no previous element in the stack, so the left edge would be minus 1. And the rectangle formed here is this. So the area of the rectangle is the minimum height, which is 2, multiplied by the right edge, which is 5, minus the left edge, which is minus 1, and minus 1, which is equal to 2 times 5, equal to 10. And this is the largest rectangle. Now we can remove this bar from the stack. Since the stack is empty now, we can add the current bar to the stack. Height is 1 and index is 5. Since this is the only element left in the stack, its right edge would be n, in this case 6, and left edge would be minus 1. So the area is minimum height, which is 1, multiplied by right edge is 6, left edge is minus 1, and minus 1, which is equal to 6. And the rectangle formed is this. And we remove this from top of the stack. So that's our final algorithm. The runtime of this algorithm is big O of n, and the spacetime is also big O of n because we are using a stack. To simplify the edge cases, instead of starting with an empty stack, we add height of 0 and index -1 to the stack. So now we never have to worry about stack being empty, and to find the left edge, we can just look at the previous element in the stack. And to handle the edge case for the right edge, we just add another element to the input array heights, whose height will be 0. So let's write the code for this algorithm. As we discussed at the end of the last segment, to handle the edge cases, we add an extra bar of height 0 to the input array. So heights.append 0. And instead of starting with an empty stack, we start with a stack that has a bar of height 0 at index -1 to handle the edge cases again. And we save the max area in this variable. Let's iterate through the given input array. For I in range of length of heights, we need to check if this forms the right edge. So the current height is height of I, while current height is less than height at the top of the stack, where stack -1 is the top of the stack and the first element is the height. In this case, the current bar at index I will be the right edge. So the first, we pop this bar from top of the stack because we found its right edge and the left edge. So stack.pop, first element will be bar height and the second element will be bar index. And the left edge will be the previous element in the stack, which is stack -1, which is new top of the stack, and the second element will be the index. So the current area is equal to height of the current bar multiplied by right edge, which is the current index, minus left edge -1. And we update max area equal to max of max area and current area. Once we have removed all the bars whose height is greater than the current bar, we add the current bar to the stack. Current bar's height and the index. Finally, we return the max area. Let's try to run this code. As you can tell, this is the most optimized approach. If you found this video to be helpful, please support by liking the video and subscribing to the channel. I will see you in the next video. Thank you.